Ladies and gentlemen, I welcome you to our presentation on modern ECU development. In our talk today, we will focus on two main topics. One of them, very trendy, modern ECU architectures, such as the centralized architectures, where technologies such as high-performance computing and adaptive Autosar come into play. And the other one, I would say quite commodity, is the functional safety, but of course in the scope of those new ECU environments. We will present you a set of reusable assets which we have extracted or derived, which can be used as puzzle pieces during your development of such safe execution of software platforms. My name is Vladimir Thelen and I am a senior consultant at Vector Consulting Services. Before we go to our reusable assets, let me elaborate a bit on what I mean by modern ECU architectures. So let us start with the classic. This will be the distributed architecture. Here it is typical that each and every functionality in the vehicle is realized in its own ECU with dedicated sensors and actuators. Normally we have one supplier per ECU and we have slightly high number of boxes which are distributed within the vehicle and they communicate with each other by vehicle bus communication. Typical here is that we have only a limited amount of data shared between the ECU. This brings us to the next evolutionary step. This is the domain architecture. Typical here, or the main idea, is that we have the complete software which is relevant to one and the same dedicated domain is bundled together in one ECU. So we have software which is relevant to different functionalities, maybe provided by different suppliers, and they share sensors and actuators which are distributed within the vehicle. In our architecture, this is provided by those slightly bigger blue boxes. And this is already a big benefit. Nevertheless, nowadays we have more and more merge of those domains. And furthermore, we have increase in complex functionalities, which again make use of many different domains. So imagine, for example, autonomous driving functionality. There, the function uses, for example, steering, braking, environmental sensors such as camera, radar, LiDAR, the infotainment system, and merely basically we can say that each and every domain in the vehicle is being used. So you see also here we get again a very distributed or a very intensive usage of multiple domains. So that's why the next step in this architecture evaluation is the centralized architecture. And the main idea here is that we combine the complete software in the vehicle and put it into one, maybe two high computational ECUs. And those make use, let's say, of smart sensors again, which are distributed within the car. And this architecture provides already a lot of benefits. So we have cost saving because we have a reduced amount of ECUs. We have very high level of software reuse. We can easily extend functionalities, and we can keep rollout ECUs in the field up to date because of the reduced, let's say, dependence on the hardware. And I would say at the moment we are past, let's say, to this domain architecture, and we are moving towards the central architectures. Let us have a look inside such an ECU. Starting with the hardware perspective, we see two main portions, the microprocessor portion and the microcontroller portion. It is essential that those two do not overlap each other, but they extend each other because of the inherently different properties. Let us start with the microcontroller. Those devices are normally less powerful but have much better real-time performance. Additionally, the availability on the market of such devices capable of high safety integrity levels is much higher, up to ASUD. That's why it is reasonable to implement the safety portion of the software into the microcontroller portion. Going to the microprocessor, we have much more PC-like behavior, which means we can use multiple operating systems in parallel. We can, let's say, dynamically install and remove software contents, which is behavior we are well familiar from our mobile devices, and we can easily establish back-end connectivity. Based on their strengths, the use cases for those two portions are different. Starting with the microcontroller, we typically have sensors and actuators connected which require very fast control loops. This would be like the sensors and actuators of a braking system. On the microprocessor side, we have, for example, sensors which produce big amount of data and benefit from the high performance computation of such devices. These are like cameras, LiDARs, radars. On the other side, also the vehicle bus communication reflects the difference in the use cases. So here in this case, we have on the microcontroller side, typically CAN, LIN, FlexRay, and on the microprocessor side, we have mainly Ethernet. Additional portion, which is also quite important, is the interprocessor communication. Depending on if we have the microprocessor and the microcontroller portion into one device, such as system on chip, or we have two separate devices, also the technology implementing the IPC might differ. Example here are, for example, shared memory or PCI Express. What is important in this case, also for the vehicle bus communication, is that the IPC needs to be reliable and safe. Let us have a look also at the software perspective. Starting with the microcontroller, we have an Autosar classic OS type running, and combined with the software components into one binary, this complete block is put into the microcontroller. Looking at the microprocessor, this looks slightly different. We mentioned before that here we might have the necessity to operate multiple operating systems in parallel, and this leaves us, let's say, with the necessity that we need the components such as a hypervisor, which have become more and more standard or established within automotive architectures. Also crucial here is that the applications are separate binaries which can be removed and installed separately from each other. And this leaves us directly with the requirement that also the communication paths need to be removed and established dynamically. So in this case, it is recommended to use service-oriented communication architecture. So on the first glance, this might look straightforward, but in real life, this is quite complex. And let us put also our second topic or second main topic of functional safety now here on top. So it is not always possible to separate functional safety and segregate it and put it, let's say, explicitly into the microcontroller. And this leaves us with the requirement that we also need to consider functional safety in the scope of the microprocessor environment, ensuring that we have a safe execution of software platform. Looking macroscopically at the safety topic, we have on the one side a product, safety, and maybe security concept available to some extent, maybe only as ideas or chunks, or even a mature or holistic safety security concept which expect the safe and secure execution of software. And on the other side, we have our final target, which is actually the adaptive Autosar conform execution platform software. To that moment, the adaptive Autosar documentation, safety-related documentation is still under development. So the core of our approach, how to bridge the left and the right side, is based or considers the already available functional and technical level documentation from Autosar, and we were able to extract or synthesize some standardized reusable assets or patterns which provide like a meta level, like a technical solution level, but still allowing a freedom for the precise technical execution. You can think, for example, which frameworks are used or which products may be from different suppliers. Due to the fact that the reusable assets are the core, or let's say the foundation of this bridge between the concept and the actual implementation, I would like to elaborate a little bit more on the procedure we followed for synthesizing those reusable assets. So this looks like, I would say, a big matrix. So this is only to give you an impression. So in reality, it looks quite bigger. On the left side, you see a very high safety category definitions. It is like safe execution during initialization or during runtime or storage of data. And then we have the corresponding expectations, which give a little bit more detail on those categories. Next are the functional safety requirements provided by the adaptive Autosar and the corresponding technical safety requirements provided by the adaptive Autosar. And we have taken those and let's say synthesized or derived this meta level of technical implementation. To that moment, we were able, let's say, to extract 7 patterns. And I would like to elaborate how those look like so that you get an impression what this pattern or this reusable asset is using 2 examples. In this case, the platform health management and separation. By the given examples, you see that the platform health management has something to do with the correct temporal execution of software, for example, aliveness. And the separation has something to do with freedom of interference between the different applications. So let's have a look, more detailed look at both of those patterns, starting with separation. We mentioned previously, maybe you recall, that the dynamic software content is one of the main ideas or main characteristics of the dynamic of the adaptive Autosar. And but taking, let's say, now the safety perspective, those different contents might be implementing, let's say, different functionalities. They might have different ASILs. Maybe coming from different manufacturers, and it is essential that those do not interfere with each other, so that no adverse effects result out of this. So the basic idea is to encapsulate or separate those in logical partitions or containers. There are different extents for these separations which are possible, and I have put 3 possibilities together. The first one on the left side is to have only one operating system, and the apps are running directly on the OS. Now, the separation is ensured by definition of virtual memory blocks for those applications, and those applications or processes, they become prioritizations. An extended version, this would be the middle one, is the bundling of apps in process containers where individual resources can be configured. So in addition here to the previous version is, let's say, that we have the possibility to introduce additional limitations. For example, CPU maximum usage can be configured for the container. And a further extension is, let's say, the bundling of process containers and applications into partitions, which are then executed on different OSs. This is the variant on the right side. Additional here is that we have explicit allocation of resources such as CPU and memory, but also hardware like peripherals, vehicle bus communications, IOs, and the separation here is realized really by this explicit and guaranteed resources and time partitioning, including hardware. In summary, key here are the resource domain partitioning and time domain partitioning. So with resource perspective, we have guaranteed availability of memory, of CPU resources, of peripherals if needed. And with respect to the time perspective, because we are in safety-related environment, we have to ensure real-time performance. That's why those processes are allocated to partitions, and those partitions are executed in partition timeframes dedicated to them. Based on this separation per design, a really interesting implication for the safety case result. And this is the case that we can provide separated or compositional safety assurance evidence. What does that mean? Let us imagine for a second that we are a theoretical braking application supplier, and our product is going to be integrated into such a high performance ECU. So let's say the overall product integrator has ensured our separation containers, meaning we have resource partitioning, we have time partitioning. So in this case, the theoretical braking application supplier does not need in their integration activities to consider if there is additionally steering, maybe infotainment, or other, let's say, functionalities or applications in this ECU, because they are segregated from each other and they can really concentrate on providing the encapsulated safety case really only in the scope of braking. The next exemplary asset that we have prepared is the platform health management. So you can imagine all scenarios relevant to the temporal and logical execution of software. So if you may, these are the not execution, the too long or too short or wrong program flow, which are considered here. And key for this asset are the so-called checkpoints, which are reported points into the control flow. So if you need to realize an alive monitoring, we can count the number of checkpoints in a certain interval, and let's say detect if the software is executed or no. If we monitor the time interval between two checkpoints and compare it with the predefined minimum and maximum time, we can identify if the execution of software takes too long or takes too short. And if we compare, let's say, or validate the logical sequence of those checkpoints with the predefined execution graph, we can identify or ensure logical supervision for the software. Let us come to our conclusion. We talked about modern ECU development evolving from distributed architecture towards central architecture. We talked that in the scope of those central architecture, the software contents are getting highly dynamic, which leads to the use of adaptive Autosar. And we saw also use cases where functional safety needs to be considered for the adaptive Autosar platform. Nevertheless, at the moment, the adaptive Autosar safety documentation is still pending. So Vector is offering here a holistic, safe and secure solution for the adaptive Autosar implementation, including the software framework on the one side and also the relevant conceptual activities on the other side. So we saw our reusable assets, and this is the core of our conceptual approach, providing the bridge between the concept and the product. And those assets, they can be used as standalone or even in combination with the software framework from other suppliers, or of course those can be used in combination with the Vector dedicated adaptive Autosar solution, which is the MicroSar Adaptive Safe. So this brings us to the end of our presentation for today. Thank you very much for your time and for your attention. And if we have awakened your interest on this topic, please do not hesitate to contact us.